Hello and welcome back to the Save It for Parts channel, where today we've got something really exciting to take a look at. I've just received this package all the way from Australia from Robinson Aerospace, and they're the makers of the RAScube or RAScube cubesat for schools, universities, and general education. Now, I've looked at educational CubeSat simulators before. I have the MySat sim up here in the case, and I've actually upgraded the MySat with a space-grade filament for the 3D printed fuselage. But the RAScube satellites have actually been launched to space before, or at least one of them has. So this is potentially some actual space-proven hardware, so that's pretty exciting. Let's open this up and see what Robinson sent us. So first off, I have the RAScube LB version 1.0. So I think this is their kind of entry-level CubeSat kit. Looks like there are some additional parts in here. We have a test bench for the RAScube V2. We have some stickers. I always tell people I love stickers, so these go on everything. We have a bunch of these fantastic remove before flight key rings. Love these things. Yeah, we have a Robinson Aerospace pen. And down at the bottom here, we have an even bigger CubeSat. It looks like this one is the V2.1. So this is their, I think their newest product and their fanciest one. Now, I don't think I'm going to get to both of these in this video. I might have to start with the simple one and then come back to this guy later, but we can take a quick look at what's in here. Yeah, we've got some circuit boards. We have another remove before flight keychain. Yeah, we've got some side panels, kind of the standard stuff that I'm familiar with from doing the MySat before. So in the larger box, we have, again, kind of similar stuff. We've got a manual. We've got what looks like an anti-static work pad here. It looks like we've got metal panel modules. We've got a radio. We've got the circuit boards. This looks really cool, but like I said, I think we're actually going to set this one aside and focus on the easier one first. So stay tuned for the V2. We will definitely be coming back to this in the future, and probably the very near future, because I'm very excited about this. But we are going to start with the LB first, because I think that looks a little more approachable. And these are, like I said, a little bit fancier than the other options out there. They are also a little bit more expensive. So this is more expensive than the MySat that I worked with before, but it should be a little bit nicer. It's designed in Australia, kind of from scratch. A lot of the modules are built in on the boards versus little plug-in modules, generic Amazon modules that the cheaper option used. So we've got all kinds of parts and accessories here. We've got antennas, including a GPS antenna. There is a little ground control board here, a little USB radio modem. We've got, yeah, more bits and parts, hardware, yeah, all kinds of stuff. We have some cabling, some batteries, and it looks like just about all of the frame pieces are included here, so I don't have to 3D print anything myself, and these look like pretty good quality. I'm not sure, these don't actually look 3D printed. These might actually be extruded or vacuum formed plastic or something. So yeah, this all looks fantastic, but before I dive into it, I'm going to have to take a look at their documentation online, and I will also read through the manual here and figure out, how do I get started with this? Well, the manual is super straightforward. It goes through every step of assembly, makes everything look pretty simple, and then at the end it jumps into the software connection, and I'll probably have to go to the software itself for that, because that's kind of where the printed manual ends. But there are a bunch of other documents online about calibration, about the Arduino libraries, technical manuals, just all kinds of good stuff. So we'll get started with the physical assembly first. Actually, I did that in the wrong order. This is the bottom plate. I was supposed to put the top plate on first, so we'll go back a little bit. right, there is our physical assembly of the satellite. So yeah, it went pretty well. I had to go back a couple times, either because I didn't read the manual, or there was one point where it wasn't super clear. It looked like this, the GPS module in the manual, it kind of implied that you have it facing upwards from the board, but then when you actually put it in place, you want to flip it over so that the white part is on top here. So I probably could have figured that out if I'd read ahead and really thought out the manual first, but it wasn't too hard to pop that top telemetry board off and just reposition the connector for the GPS module. The only other little issue I'm noticing is a couple of these side rails are loose. Yeah, a couple of these didn't really lock in completely to the side panels, so yeah, it's mostly just this one that's kind of wiggly. Yeah, not too big of a deal. It's held together here with the screws. The side rails are mostly just to align these corners. But yeah, otherwise, I think this is ready to hook up to the computer. And yeah, we'll plug in the radio module here and check out the software and go to the next step. Now there's one circuit board that I didn't use. This is the prototyping module. It's basically just all of the pinouts exposed from the bus here. So we have SDA, SCL, clock, all the usual serial stuff, TX0, RX0. Yeah, we've got a bunch of pinouts from the Arduino system that runs the onboard computer. And then we have a 5-volt rail and ground. We also have a 3.3-volt rail and ground. So you could put other modules on here. You could put sensors on there, a camera, other stuff. Basically, it is up to your imagination. So this is pretty cool, that you not only have the basic CubeSat bus and structure, but then you can design and install your own experiments. There's a few other spare parts. There are some more standoffs. So if we were going to mount that prototyping board, we would use the extra standoffs. And then there are spares pretty much of each piece. So in case you lose something, there are spare standoffs. There's a spare jumper for the power system. There are 2 little wrenches in case you lose one. This is definitely designed for students or adults like me who are prone to losing small parts in the process of putting something together. All right, we have some telemetry coming through on the web panel here. So we've got orientation, acceleration, gyroscope, magnetometer, pressure, altitude, we've got voltage, all kinds of stuff here. Let's see if I pick this thing up and mess with it. Oh yeah, the gyroscope responds, the magnetometer responds, orientation, and it's using 915 megahertz, so it's using essentially LoRa frequencies, an unlicensed band. If we were actually going to launch something like this into space, we'd probably want to use some other frequency. There are some LoRa satellites that use like 433 megahertz, European band, and then otherwise a lot of these little satellites will use ham radio bands, so 2 meter VHF or 70 centimeter UHF. I'm not sure how easy it is to swap out another radio, but that could be something interesting to do with the prototype board. So it's pretty cool that the magnetometer is sensitive enough to pick up when I hold a metal object near the CubeSat. That magnetometer really responds. I could potentially use that to detect something. Like if we were out in space, we could try to detect, I don't know, other satellites or metallic asteroids or something cool. Let's see, we can download the raw data. So I can download sensor data as a CSV file and look at this offline, look at this with another application. If we wanted to throw this into Excel or OpenOffice, if we wanted to process this with some other script, we could get some other, more powerful processing tools pulled up and do something with the raw data. We've got settings here. We can change the UI version, USB. We can change some stuff like the bandwidth, enable development data. That's already turned on. Don't think I'll mess with that right away. But yeah, very, very straightforward telemetry dashboard, very easy to use. I don't fully know what I can do with it yet, but it's definitely a great way to learn, a great hands-on way to learn stuff. And I learn much better by doing hands-on stuff than with just computer simulations or reading a textbook. One thing this can help me learn more about are the radio signals and data structures used by small CubeSats on the LoRa 915 megahertz band. So I'm going to use my RTL SDR software-defined radio, and I'm going to borrow the 915 megahertz antenna that came with the RAScube serial radio. All right, so I've pulled up SDR++, the software that I normally use with these RTL SDRs, and I've tuned into the 915 megahertz band, the ham radio 33 centimeter band. Now I'm already noticing some blips of data here and there, and those are probably other LoRa devices. I've got a Meshtastic node on the roof. I've got other devices around the house that probably use this same band, and then the neighbors probably have some stuff that use this as well. So it is not a completely quiet band, at least not here in the city, but it's not overwhelmed with noise either. So if I go ahead and pull out that remove before flight pin to activate the RAScube, we should start seeing something happening. And there we go. We are getting telemetry data. Well, we were getting it, and I moved my little, I moved my slider here and it jumped off. I'm actually going to move the satellite farther away from the antenna because I think I'm getting a reflection here. Yeah, this is something that's actually a little weird. When I move my slider, when I move, the apparent frequency jumps around. Maybe I've got the gain turned up too high and it's overloading things. So I'm already learning things about my radio setup here in that I probably don't have things set up quite right. All right, I think I've got this figured out. We have the RAScube LB telemetry signal centered at 923.2 megahertz, and this is the main signal. If I move this around, it stays at 923.2. So the signal that I was seeing earlier down around 915 was a reflection because I had the gain too high. I had to move the CubeSat out to another room in the house and turn the gain way down because it was just overloading my RTL SDR. And that's kind of a danger of having your gain set too high. Normally when I'm looking at satellites up in space, I have the gain like maxed out because you're trying to listen for something 100 or 200 miles up above the Earth's surface. When it's in the next room, it is kind of overpoweringly loud. And when it's in the same room, I could potentially cause damage to my SDR this way. So definitely don't want to operate this thing right in the same room as the SDR, and definitely not with the gain turned up very high. So anyway, this is what the LoRa signal looks like. We could actually listen to this and see what it sounds like if I turn on the audio here. Yeah, it doesn't sound like too much. It's just little pulses of data coming through. And it is a pretty constant stream of data. It's not just a little blip here and there like Meshtastic or other messaging protocols are. This is kind of hogging the band. So if you had something else operating on this frequency, that would interfere with the RAScube, or vice versa. The RAScube satellite could potentially interfere with something else on this 923.2 megahertz frequency because it is transmitting essentially constantly. And there might be a way to retune this. If I go into the Arduino settings, if I go into the serial radio protocol settings, we might be able to retune it. We might be able to change the bandwidth or change the duty cycle. I don't quite know how to do all those things, but it's definitely interesting to see a near constant duty cycle for something like the RAScube versus what we saw earlier with the just little blips of data from Meshtastic. And like I said, we're getting reflections here all over the place, even with the gain turned way down, even with the thing in the next room. This little signal on the left here is kind of a ghost, a reflection because it's overloading things. If I scroll around, that ghost goes away. If I scroll back down to 915 megahertz, if I turn the gain up, we'll still see that thing. So yeah, we're seeing it here. We're seeing another ghost of the overloaded signal. So this is a great way to learn about an SDR, software-defined radio's response to overpowering signals to see what does it do, what does it look like on the screen. And as I said, I've seen stuff like this before. When I'm looking at satellites, I've seen ghost signals like that all over the place when I've had my gain turned up too high. Generally, those aren't actual satellites. Generally, I'm seeing ground-based interference from other stuff on this ISM band, other stuff like Meshtastic, cell phones, just other interference from around the house. So really a good learning experience to see what that looks like in real life. So the radio module on this is the same as the one on the receiver. It's this RA01SH. It says it has an output power of about 22 dBm, which corresponds to about 0.15 watts. So this is really not very powerful, but it's still powerful enough within the same house to overload the SDR. I was using the same antenna that the receiver had on the SDR, so they're matched pretty well. And I found some of the data sheets on that RA01SH LoRa module. So it talks about some of the modem options, some of the modulations, the frequency, all the stuff you'd need if you're going to use one of these modem chips in your own project. Now, the manual does note that this particular product is not really designed to go into space. This is a educational platform, much like the MySat, much like some of the other CubeSat kits out there. It's a learning tool. It's not a real satellite, although it does, again, have a lot more realistic parts than the MySat. The bus is a lot more realistic. Some of the sensors and telemetry seem a little bit closer to launch-ready hardware. And when we get around to the RAScube V2, that one has actually flown in space, so that one is much closer to space-based hardware. Other things that are different about this for space use, beyond the frequency and possibly some of the radio stuff, the manual actually mentions back in the safety warning section, the one that everybody ignores, it does say that this is designed to be used in class on a table or a bench. It is not designed for launch into space. It would not survive temperature or radiation environment in space. It's not waterproof. It's not really environmentally sealed. Not that there's a lot of water in space, but there are possibly some considerations with icing or putting the thing into a launch vehicle before and during launch. It's going to pass through a lot of different pressure and temperature gradients. It could get some humidity issues. And then, of course, the sensor suite on this is designed more for in-atmosphere use. We have barometric data coming from this, which is obviously not super useful in space, but would be useful on something like a high-altitude balloon. And the manual does mention that the RAScube can be used on flights with weather balloons, subject to regulatory approval. So that's pretty cool if you want to simulate something approaching a space mission, although I always get a little twitchy when people call weather balloons near space, or they say, oh, we sent so-and-so to space on a balloon. It's not space, it's just really high up in the atmosphere, but it is still kind of the closest you can get without a $50,000 budget. And the manual also mentions that it's designed for ages 10 and up. I think younger kids could handle this, but yeah, I would stick with adult supervision. If you're giving it to a precocious 6-year-old or something, yeah, I think they could figure this out pretty quickly and get online and use the telemetry interface. But yeah, it's very straightforward. Like I said, very cool as an educational model. Not a lot of barrier to entry with this. Personally, I would love to do a weather balloon, and this is definitely kind of suited for that. The telemetry that it's sending down is giving you the altitude, it's giving you the pressure, it's giving you the GPS coordinates. So if you were going to track this on a balloon flight, it is very, very well suited for that. And then things like the magnetometer could tell you potentially what kinds of geology you're flying over. If your weather balloon passes over a mountain range, your magnetometer might be able to pick up ore deposits, metallic deposits. That would be kind of fun. The gyroscope and acceleration data can tell you how it's flying, if it is being buffeted around by the wind, if it's tumbling. When it's coming down on a parachute, it could give you information about the acceleration or descent rate. Yeah, lots of cool stuff there. I don't have a weather balloon at the moment. That's kind of on the list, but might be down the road a little bit. We won't be doing that in this video or anything, but it is on the to-do list, so we'll see what happens down the road. I think the batteries here are probably also not space rated. I don't think you generally launch a CubeSat with AA batteries, but you could easily desolder this, put on some kind of other battery pack. You could add solar panels to this. You could swap out the side panels with panels designed for solar panels or integrating solar panels. And if you were doing your own sensor modules or your own camera or something like that, you could integrate the camera with the built-in cutouts on the side panels, or you could again design your own side panels for sensors or cameras to clip into. Very flexible platform, and they do give some of the specifications on the side panels and the corner pieces on the website. CubeSats are kind of a standard platform. They're a standard educational form factor, so there are a bunch of models like this that you can print out, 3D printed or laser cut. You can do metal. We saw the upgraded version, the V2 has metal side panels, but you could do that yourself if you had a CNC machine, if you had access to a water jet cutter or a laser cutter. And RAScube actually gives you a couple 3D print files or links to 3D print files in the documentation, so you can print out a new one unit cube here, or a 2-unit cube, which is essentially 2 of these cubes stacked. So it's a little bit longer. You can put more stuff in it. You could put additional prototyping boards in. Lots of options with something like this. Lots of flexibility. I realize this video might sound a little bit like an advertisement, but other than giving me the free product, they're not paying me to say anything about the RAScube. They're not paying me for the video. I always do try to make sure my reviews, my product evaluations are fair and honest. And honestly, I have found almost nothing wrong with this thing. My only complaint was this little wiggly edge, and really you could fix that with a little bit of glue. So yeah, I have not found any issues with this. I have not had any problems with it. And I honestly, genuinely think this is a cool product. And heck, it is a space-related product. It is a save-it-for-parts-related product. This is right up my alley. This is not just some random Amazon device that I'm reviewing. This is a satellite, so I am genuinely excited to share it with everyone. So in addition to the hardware, Robinson also has these lesson plans that teachers can use to incorporate into their classroom activities. So they actually gave me a password for this section so I could check it out. I definitely won't have time to go through all these lessons, but I am going to check a few of these out. We could try to graph things like the time and temperature relationship. So we could graph this different ways. We could see a linear rise in the temperature over time. One of the lesson plans relates to spinning the satellite and measuring the motion from the sensor data. So if we put this thing on a rotating platform and we look at the magnetometer and gyroscope values, we can kind of get a sense for the rotation speed. Another lesson was basically placing the RAScube on a motorized platform, which is a little more reliable than just moving it by hand the way I'm doing, but moving it towards some kind of a source and looking at the magnetometer values to try to determine how close is it to that metal object or signal source. And there's another lesson plan that talks about looking at the radio signal, which we've already done with the SDR, but the lesson plan discusses how to do it with an oscilloscope. Now, since this has an Arduino microcontroller as the onboard computer, the OBC, the brain, there is a USB port here, so we can interface it directly to the computer. So I need to update my Arduino IDE to use the RAScube libraries. So I'm going to go ahead and open this calibration file just as a starter. And we want to make sure that we're using the correct Arduino device. And I need to install some more stuff for that. So we can go ahead and upload this new file to the cubesat. So we have a red LED indicating that we should be ready for calibration. So we're supposed to leave it flat on the table here and first just unplug the USB. So the LED is supposed to turn blue and it will do a calibration. We go through a couple different colors. And it says do not stop rotating until the LED turns green. It has turned green, but I haven't finished rotating. And I'm going to assume that we have now calibrated the compass and the gyroscope. So now we want to plug this back into USB and re-upload the default firmware so that it does all the regular RAScube stuff and isn't stuck in calibration mode. All right, it looks like everything is working on the telemetry. As I move the satellite around, we can see all the changes in the data from the gyroscope and the accelerometer, the magnetometer, the compass. I don't know if the data is better or more precise now that we've calibrated things, but theoretically, we've improved it by running those calibration steps. If we wanted to put our own custom firmware on here, if we were using the prototyping module with any custom sensors, we could do it that same way using the Arduino IDE, uploading a new sketch, recompiling it for the Arduino Zero microcontroller on here. It's fairly standard stuff. I've done that with other Arduino microcontrollers. Now it's a little bit more of an advanced step or advanced process to update the firmware versus just assembling the thing and turning it on. And it does come with the default firmware that works perfectly well. But if you wanted to do anything special or custom with it, it's totally an option. And that is something I'd like to play around with in the future. I would like to learn more about how to program Arduino devices, how to integrate sensors, how to add things to this. I did dig through my box of Arduino parts and I didn't find any sensor modules that I thought would really work with this. I do have some environmental stuff. I do have some I2C sensors, but most of those are on my Raspberry Pi Picorder. So I might need to order some things for this, but again, that might be a future video. So this has just been a quick overview and intro to the RAScube LB. Yeah, I really like it, and I think this would be a fantastic addition to STEM classes, to science classes, anybody interested in learning more about space, science, satellites, and just all of the stuff you can do with the sensors is a lot more interesting and engaging to kids. Even if you don't do space-related stuff directly, having it in a CubeSat package probably makes it a little more cool. There's more of a cool factor for kids if they can say, hey, I'm learning about science with a satellite, versus maybe just learning about science and sensors and electronics with a pile of parts on a bench. Might not be quite as engaging as actually being able to hold something that you can imagine going into space. Anyway, I'm going to wrap this video up. I will throw some links down in the description to Robinson Aerospace, to the RAScube LB, as well as one of their partners who does the launch box, the LB edition here. And that one is aimed specifically at education. And if you're in Australia, I think there are even grants available where you can get a hold of one or more of these for free for your school. So you don't even have to pay for these. Again, in Australia, I think if you're in the US, if you're in other countries, you probably have to figure out your own grants or your own funding for it. Thank you again to Robinson for sending me the RAScube LB. It's been a lot of fun. I hope to come back to this one in the future. Like I said at the beginning of the video, they also sent me the RAScube V2, so we will probably be looking at that next in an upcoming video. Check out my other videos if you want to see more satellite-related topics, including listening to actual satellites up in space. And as always, thank you to everyone out there for watching, and we'll see you next time.